everyone, welcome to our low-temperature thermochronology online class. We will continue the Chapter 4, Uranium, Cerium, Helium, Thermochronology, Analytical Techniques. Today, we will finish the second session about crystal characterization. The characteristic X-ray-based techniques will be introduced in this lecture. X-rays are generated by inelastic scattering when the electron beam interacts with specimen atoms. Two basic types of X-rays are produced. One is the characteristic X-rays, which result when the primary electron ejects electrons from the inner shells of the specimen atoms. These are characteristic of the atom of the element. Characteristic X-rays are used for X-ray analysis. The other is the continuum X-rays, also called continuous X-rays, which result when the primary electron interacts with the nucleus of the specimen atoms. For continuum X-rays, they are just background and can't be used for the identification. When the electron beam interacts with specimen, a vacancy can be created in an inner shell of a specimen atom once a high-energy beam electron, backscattered electron, or high-energy secondary electron strikes an electron of an inner shell, knocking the electron out of the atom. The specimen atom has a vacancy in the inner shell and is ionized, which will be in an unstable state. An electron from a higher shell falls to the vacant inner shell. The specimen now has amount of excess energy equal to the difference between the two shells. This energy difference is commonly emitted in the form of an X-ray, resulting in the characteristic X-rays. The energy and the wavelength of the X-ray produced are characteristic of the element and are related by the equation lambda equals to the ratio of 1.2398 to E, where lambda is the wavelength in nanometers and E is the energy in 1,000 electron volts. According to Moseley's law, the energy of a given characteristic X-ray line varies approximately as the square of the atomic number of the emitting element, as shown in the figure. For the characteristic X-rays of each element, they have the unique energy and wavelength. Characteristic X-rays are much more useful. Measuring either the energy or wavelength of the characteristic X-rays enables the investigator to determine the elements from which the X-rays were emitted, since no two elements have exactly the same energy difference between electron shells. There are two kinds of X-ray spectrometers. The energy dispersive spectrometer, called EDS, records X-rays of all energies effectively simultaneously and produces an output in the form of a plot of intensity versus X-ray photon energy. The detector consists of one of several types of device producing output pulses proportional in height to the photon energy. The wavelength dispersive spectrometer, called WDS, makes use of Bragg reflection back of crystal and operates in serial mode, the spectrometer being tuned to only one wavelength at a time. Several crystals of different interplanar spacings are needed in order to cover the required wavelength range. The spectral resolution of WDS is better than that of EDS, but the latter is faster and more convenient to use. X-ray spectrometers attached to scanning electron microscopes are usually of the EDS type, though sometimes a single multi-crystal WDS fitted. A scanning electron microscope equipped with an energy dispersive spectrometer is excellent for rapid qualitative analysis of unknown samples. Like the SEM, Electron microprobe is a microbeam instrument, but it is an important tool for quantitative chemical analysis and compositional imaging. Electron microprobe instruments typically have two independent X-ray detection systems fitted with up to 5 wavelength dispersive spectrometers, and often have an energy dispersive spectrometer as well. The use of WDS provides greater analytic precision, superior peak resolution, and lower detection limits down to a few ppm. As shown in the right figure, the electron microprobe traverse demonstrates that not only do the backscatter electron image and CL images reveal detail regarding different regions within the zircon, but also that the concentrations of the hafnium, yttrium, and uranium vary considerably within the backscatter electron and CL revealed regions. The compositional zoning of minerals can be further demonstrated by elemental distribution maps obtained by wavelength dispersive spectrometer in EPMA. For example, the EPMA imaging of fluoride accurately reflects the compositional variations in the single grain and reproduce the zonation patterns seen in the backscatter electron image and CL images. A summary of the second session of the Chapter 4 mainly used analytical techniques of the crystal characterization include the light microscope and the scanning electron microscope or electron microprobe. The shape and size of each crystal can be observed and measured by the light microscope, and details about internal structures of the crystal will be investigated by the backscattered electron image, cathodoluminescence image, and X-ray spectrometers in scanning electron microscope or electron microprobe. That's the end of the lecture today. Thank you for your attention.